Hi, I'm Mr. Christian and I'm going to discuss about plate tectonics and Earth's history. Plate tectonics, together with seafloor spreading, supports the continental drift theory. So our main discussion for this topic will be all about continental drift theory and its subcomponents. Earth's history and geologic timescale will be discussed in another session. Regarding with continental drift theory, what is continental drift theory? Based on the illustration you are seeing right now, you have seen a mountain, which is broken down into two different parts. Okay? So continental drift is related to this idea, wherein continents are drifting apart. It was believed that there was once a supercontinent called Pangaea that slowly drifted apart simply because of the presence of convection currents allowing the lithospheric plates to move. It's either they will collide, or they will drift apart, or they will slide past against the other. So these are the main movement of the continents. Here, continental drift refers to how continents shift position on the Earth's surface. As what you have noticed here, the supercontinent Pangaea, or a single giant landmass, slowly separated. On the right side of your screen, they are now located on a location wherein they are arranged further apart from one another. So continental drift theory was proposed by Alfred Wegener, wherein he showed pieces of evidence of horizontal or lateral movement of the continents in his continental drift theory. Talking about horizontal and lateral movements of continents, it's the random shifting. It's the continuous movement of continents. Alfred Wegener thought that continents have drifted around the world and have once formed a giant landmass, or a supercontinent called Pangaea. Now, this Pangaea slowly drifted apart from one another, and there are several reasons which causes the separation of the supercontinent Pangaea, such as earthquake, extreme volcanism, and other geologic activities. Alfred Wegener proposed several evidences of continental drift theory which will support his claim. First, he proposed the geographical evidence. Next, the biological evidence and the climatic evidence. Under geographical evidence, Wegener referred the idea as the jigsaw puzzle fit of the continents. As what you have noticed here on the right side of your screen having the green color, the coastlines of South America perfectly fit to the coastlines of Africa. That's why it's like a puzzle, wherein Wegener referred to it as the jigsaw puzzle fit. Okay, so the coastline of the other continent is the perfect fit to the coastline to the other continent. Okay, so going back, there are different continents within the planet. Now, there are several continents having similar coastlines. As what you have noticed here, the coastlines of South America is perfect fit to the coastlines of South Africa. Okay? And the coastlines of Africa, it's a perfect fit within the coastlines of the European countries. Okay? And there are also from the European countries wherein they tend to fit in the northern portion of America. Okay? So as we tend to trace them, they seem to fit with the other continents. Okay? So there are portion of them wherein they tend to fit with one another, okay, allowing them to form a single giant landmass. Okay, so regarding here, we have a much closer arrangement of the continents. As what you have noticed here, there are coastlines having similar patterns. That's why Wegener concluded that they may be a single continent before that slowly drifted apart, becoming into 7 major continents. That's why, under the geographical evidence of Mr. Wegener, he stated that the coastlines of continents seem to fit with the coastlines of the other continents. So this is one example of the geographical evidence as proposed by Mr. Wegener. And also the presence of mountain ranges having similar rock types and age but separated by vast oceans, like that of the Caledonian Mountains and the Himalayan Mountains. So Wegener observed that a portion of the Caledonian Mountain is separated to continent A, while a portion of the Caledonian Mountain is separated to continent B. But how come? They have similar rock types and they have similar age. So this strengthens the idea of Wegener that they may be a single landmass or a single mountain range wherein they tend to separate as the continents drift apart. Next, Wegener proposed the biological evidence, stating that a fossil is any trace of an ancient organism that has been preserved in rock, under sedimentary rock. For example, Glossopteris. The Glossopteris was a plant that lived 250 million years ago, later on been found in the rocks of Africa, South American continents, Australian continent, India, and even from Antarctica. So Glossopteris is a plant, it cannot travel, but how come it is widely distributed? Okay, it doesn't have legs to travel, it has its specific roots, holding itself firm in a single location. But the arrangement of Glossopteris fossils are widely distributed among the continents of Africa, South America, Australia, India, and Antarctica. So the occurrence of Glossopteris on these widely separated land masses convinced Wegener that Pangaea had existed. Here, this is an example of Glossopteris leaf, okay, trapped in a sedimentary rock. How come a Glossopteris leaf from Africa is capable of moving towards another continent, such as Australia, South America, India, and even in the Antarctica? Okay, so they're just plant, but they are widely distributed all throughout the globe. Okay, that's why Wegener believed that they may be a part of a single landmass wherein they tend to dominate on a specific region. By the time continents slowly drifted apart, Glossopteris plant is trapped on a certain continent. Seems like they are widely distributed. Okay? Aside from Glossopteris, Wegener also found another fossil. Okay? Freshwater reptile Mesosaurus and Lystrosaurus. Okay, so here we have the fossil of Mesosaurus in South America and the fossil of Mesosaurus in the southern portion of Africa. Wegener wondered how come there are similar species found in two different locations. Okay, so we have Mesosaurus here in South America. We also have Mesosaurus here in the southern portion of Africa. In between them is a large ocean body. So Mesosaurus cannot swim simply because it's a freshwater reptile. Okay, so it cannot swim between a large ocean body. Okay, because it can't survive. This is salt water. Its main habitat is fresh water. That's why Wegener tends to wonder how come Mesosaurus was capable of crossing different continents where in fact it is very far. So Mesosaurus could possibly be distributed in a single portion of land which later on breaks apart into South America and Africa. Okay, so these fossils have also been found in places now separated by oceans. Neither reptile could have swum great distances across salt water simply because they will die. They can't swim, they can't survive longer in a saltwater environment. So Wegener inferred that these reptiles lived landmass that has since split apart. So this is the distribution of Mesosaurus, Cynonathus, Lystrosaurus, and the Glossopteris. So orange for the distribution of the Cynonathus, blue for the Mesosaurus, we have green for the Glossopteris, and brown for the Lystrosaurus. There are fossil evidence which is similar across different continents. That's why Wegener tends to ask a question. How come there are similar species from different continents? Possibly, these species were part of a single giant landmass supercontinent that are carried as the continents drifted apart and they die in a specific continent. So, this evidence supports the geographical evidence of Alfred Wegener. Another evidence Alfred Wegener proposed is the climatic evidence. As continent moves toward the equator, its climate becomes warmer. As a continent moves toward the poles, its climate becomes colder. But the continent carries with it the fossils and rocks that formed at its previous location. So good example for climatic evidence is that we have glacial striations. The glacial period also left glacial striations or scratches as glaciers move across on the underlying bedrock of the continents involved. Okay, so let's say for instance we have giant ice blocks here. Okay, so we have blocks of glaciers. Okay, so here, let's say for instance, we have blocks of glaciers trapped above a bedrock. Since the bedrock continuously moves, so as the glaciers. Okay, so the bedrock below is moving, so as the glaciers above. As it continues to move, the interaction releases glacial striations. Okay, so the picture you're seeing right now contains several scratches from the glacial striations. So meaning to say, it might be that this bedrock was exposed to a very cold climate and later on moved to a warmer climate, melting the ice, leaving the striations behind. Okay? So here we have several striations above on the surface of the bedrock. So plate tectonic states that the Earth's crust is located on top of a viscous and mechanically weak layer, therefore allowing the crust to move, and later on the crust moves due to the convective forces generated within the asthenosphere. Okay, so within the asthenosphere, it is also fueled by the internal layer of the Earth's core. So the main source of the Earth's mechanism to move is coming from the outer core. So the convection currents from the outer core allows the convection currents of the mantle to take place. Since the mantle is floating above the outer core, when the outer core moves, the mantle moves as well. And the crust, it's floating above the mantle. By the time the mantle moves, the crust moves as well. So it creates a domino effect. If the outer core moves, so as the mantle. If the mantle moves, so as the crust. So that's why there is a continuous drifting of continents from plate tectonics and from the convective forces coming from the core and the mantle. Seafloor spreading as well is a product of movement of the lithospheric plates. Okay, so the oceanic crust is moving away from the ridge. Okay, when we say ridge, it's a portion wherein the magma tends to be released on an Earth's crust. So seafloor spreading showed that the ocean floor is split along the ridge when the magma rises to form new ocean floor. Let's say, for instance, this is the ocean floor. So the magma finds its way out. Upon exposing the magma to the atmosphere or to the water, magma cools and hardens, and later on it pushes the crust away from the ridge, creating new crust. Okay, so the crust located near the ridge is considered to be new crust. Okay, while the crust located away from the ridge is considered to be as the old crust. Okay, so because of this, rocks found near the ridge are younger, so we have the new crusts, than those that are found farther away from the ridge. When the magma at the ridge crystallizes, the magnetic polarity of Earth is also preserved. Okay, so polarity is being referred as the magnetic arrangement of a particular crust. Okay, when we say magnetic arrangement, it refers to the pattern wherein a certain magma being released on the Earth's crust will create a positive magnetic polarity. Okay? And later on, newer magma will be released, pushing the positive magnetic polarity away from the ridge. Okay? Until such time, it will be replaced by another polarity as the magma continuously oozes out. If there is a magnetic reversal, then the positive magnetic polarity will be reversed into negative magnetic polarity as the magma continuously oozes out from its source, from the ridge. So here we have the new crust, this one, new crust, and we also have the older crust. Why is it considered to be older crust? Simply because it is situated away from the ridge. Okay? So here, during volcanic eruption, let's say for instance we have the mid-Atlantic ridges. Okay? In the mid-Atlantic ridges, there are continuous volcanic eruption happening. There is a continuous oozing out of magma on the surface of the oceanic crust within the seafloor. Okay? So when magma comes out, it provides newer crust. And it pushes the other crust away from the ridge. As they go far away from the ridge, it gets older and older. Okay? And later on, the oldest crust will sink and gets melted again. Okay? So this portion here, let's try to dissect our seafloor. This portion here is the youngest oceanic crust. This portion here is the older oceanic crust. Okay? And this portion here is the oldest oceanic crust. As what you have noticed here, there is a subduction zone. A portion wherein the oceanic crust meets the continental crust. Since oceanic crust is much denser, it's much heavier, then oceanic crust tends to sink than the continental crust. Okay? So the oceanic crust tends to sink within the subduction zone. Okay? And in the subduction zone, the oceanic crust, the oldest oceanic crust, meets the magma. And the magma recycles it, allowing it to rise again, creating a younger crust as it cools and hardens. So it's a continuous cycle wherein crust is also being recycled, creating the younger crust and recycling the older crust. So this is considered to be as seafloor spreading. Okay? Now, we also have magnetic reversal. So magnetic reversal is being manipulated by the outer core. The convection of the outer core allows the magnetic reversal to take place. So we have two poles. We have the geographic pole and the magnetic pole. So let's say for instance, this one here is the geographic feature, having the geographic north pole of planet Earth and the geographic south pole of the planet Earth. Inside the planet, we have the magnetic field, which is being regulated by the inner and outer core, specifically the convection currents of the outer core. Excuse me. Now, within the convection currents of the outer core, magnetic pole can shift it may be that this north magnetic pole and south magnetic pole can shift into opposite locations, such as the north magnetic pole is located on the southern portion of the globe, and the south magnetic pole is being located in the northern portion of the globe. So there is a 360-degree shift. Okay, 360. No, 180-degree shift of the magnetic poles. So what causes the shifting of our magnetic pole? What causes the magnetic reversals to take place? Okay, so magnetic reversals, once being disturbed by the sun's harmful solar flare, then it will create a disturbance within our magnetic pole, creating a shift within the north magnetic pole and the south magnetic pole. Okay, so geographic pole, they are stationary, while the magnetic pole, they are continuously moving. Okay, they are continuously shifting from time to time. Okay, depending on the conditions of our environment within the solar system. Okay, now here we have magnetic reversal. Okay, the normal polarity is usually positive, and the reversed polarity is usually negative. Okay, normal, reversed. So let's say, for instance, in our mid-ocean ridges, the magma here, the magma comes out towards the surface of the oceanic crust. So the magma, as it cools and hardens, it creates a new seafloor. It creates a new oceanic crust and pushes the older oceanic crust away from the ridge. Okay? Now, by the time, let's say for instance, after 2.75 million years, there is a new polarity within the Earth's crust. When magma comes out, it brings with it the normal polarity or the positive polarity. So it hardens, creating the new crust and pushing the once new into a location wherein it is farther away from the ridge. The once new crust is now considered to be an older crust. Okay? So here we have seafloor spreading. So from new, this one, here, new to old. So naanatay bag-o diri. And later on, seafloor spreading continuously takes place. After 0.78 millions of years, another magma oozes out from the ridge, creating another crust, having itself a reversed polarity. So we have new, old, oldest. New, old, oldest. Okay, so until such time the seafloor tends to expand, and it will reach to a point that those oldest component gets subducted and melted, eventually becoming a part of the magma, and later on gets recycled and be created into a new crust. Okay, so magma usually comes out from the ocean ridges. Okay, within the ocean ridges, there are tectonic activities happening simply because of the volcanic activities, simply because of the seafloor spreading. Okay? Now, mid-ocean ridge or mid-oceanic ridge is an underwater mountain range formed by plate tectonics. This uplifting of the oceanic floor occurs when convection currents rise in the mantle beneath the oceanic crust and create magma where two tectonic plates meet at a divergent boundary. Okay? So when we say divergent boundary, the seafloor tends to break apart, allowing the magma to rise, creating a new oceanic crust. Okay? So we have the divergent boundary. Let's say, for instance, they tend to move away from the other. As they move away from one another, it becomes like this. Okay? Divergent boundary. It becomes like this, creating gaps in between them, allowing the magma to rise within the ridge. Okay? As it hits the surface, the magma cools and hardens. As it cools and hardens, it creates the new oceanic crust since it is found near the ridge. Those crusts away from the ridge are considered as old crust. Okay? So this is mid-ocean ridge. Okay? The continuous formation of oceanic crust. Okay? So mid-ocean ridges of the world are connected and form a single global mid-oceanic that is part of every ocean, making the mid-oceanic ridge system the longest mountain range in the world. Okay? Wala na sa continental crust. Okay? It is not found in the continental crust, but the longest mountain range in the world is found within the oceanic crust. And they are much taller than the Himalayas. They are much taller than the Mount Everest. Okay? And they are much longer than the Mount Everest regarding with its mountain range. Okay? Now, the mid-ocean ridge is found in this specific red lines here. Okay? These are series of mountains growing underneath the ocean. Okay? So, as they continue to move, as they continue to emit magma, there is a continuous movement of the lithospheric plates. It's either divergent, it may be transform boundary, or it may be we have convergent boundary as well. Okay? So because of the mid-ocean ridge, but take note mid-ocean ridge is literally created from the divergent boundary. Okay? But upon the interaction of different lithospheric plates, they may produce convergent, transform, or divergent boundary. But the formation of mid-ocean ridge is being regulated by the divergent boundary, allowing the separation of two crusts and the rise of magma in between them. Okay? So, plate boundaries. There are three major plate boundaries. We have convergent, divergent, and transform. Now, for convergent boundary, these are boundaries where two plates move towards each other. Okay? So a convergent boundary is also known as the destructive margin, since it is where collision between two plates occur. Okay? So convergent boundary. Now, there are three types of convergence. oceanic convergence, oceanic continental convergence, and continental convergence. Okay, so here let's have the oceanic convergence. So for the two oceanic crusts collide, one crust sinks underneath the other. This triggers the melting, leading to the formation of volcanic arc island. Since they collide with one another, there is friction, and this friction causes extreme heat and pressure, melting the oceanic crusts. Okay, as it melts, it gets lighter, and heat tends to escape from the inner side of the crust towards the outer portion of the crust, creating volcanic island arcs. So volcano serves as a vent wherein heat will be released from the internal portion of the planet. So due to oceanic convergence, a trench is formed and a volcanic arc is formed. Meaning to say, since they are dense regarding with their mass, but they are made up of some older, some newer crust, and a portion of them needs to sink. Usually the densest part or the oldest crust tends to sink underneath. Okay? So we have the subduction zone. The subduction zone forms the trench, and it allows a specific oceanic crust to sink at the bottom. As it sinks, it gets melted. As it gets melted, then it forms a magma, allowing it to be released on the surface, creating volcanic island arcs. So trenches. What are trenches? Trenches are features of the ocean floor that are present in both oceanic and oceanic continental boundary. So here we have a subduction zone. So the subduction occurs at the trenches, therefore these are characterized as the deepest part of the earth. Okay, so we have the trenches. Trenches are formed because of the existence of the subduction zone, the sinking of a denser crust. Okay, now next we have another type of convergence. We have the oceanic continental convergence. Okay, so the oceanic crust meets the continental crust, okay, forcing the denser oceanic crust to sink beneath the continental zone. Partial melting occurs, leading to the formation of volcanic arcs as well, okay, such as this one. So we have oceanic continental. Since oceanic is denser, then the oceanic crust tends to subduct, creating trenches and sinking below the continental crust. Okay? Next we have continental convergence. Here they have similar density. So two continental plates collide, but instead of sinking one plate beneath the other, folding occurs and mountain ranges are formed. They tend to collide, rising above, folding upwards, creating mountain ranges. Okay? So instead of sinking, since they are usually lighter, so continental convergence, they tend to collide, folding upwards, creating mountain ranges. Okay? So this is continental convergence. Next we have the divergent boundary. Is the opposite of convergent boundary. Okay? two plates move away from each other, forming a new land. Thus, it is also known as a constructive margin. So the ocean ridge system is a divergent boundary where new ocean floor is produced as magma rises, pushing the older rocks aside. So let's say, for instance, when crusts move away from the other, magma rises in between. As the magma rises and cools, it hardens, forming a new oceanic crust, or forming a new seafloor, or forming a new crust. That's why it is considered as constructive, because a new ocean floor is produced from the divergent boundary, such as this one. Okay, so here there's this ridge here, the exit point of the magma. As the magma tends to exit within the ridge, it pushes the older oceanic crust away from the ridge. Okay, as it successfully enters the vent, then magma gets interacted with water, allowing it to cool down on a much faster rate, hardening, creating a new seafloor, or creating a new oceanic crust, pushing the older oceanic crust away from the ridge. Okay, so this is considered as divergent boundary. Next, we have the transform fault boundary. So it is also known as the conservative plate margin, since two plates just move past one another, neither creating nor destroying land. It is usually at the transform fault boundary where earthquake epicenters are found, because the rocks tend to break and not fold or sink, okay, like in the convergent boundary. But within the transform fault boundary, they tend to slide past against the other, creating the strongest earthquake, such as the San Andreas fault. Okay, as they tend to slide past against the other, it creates friction, and that vibration produces the strongest earthquake compared to the other boundaries. Okay, compared to convergent boundary, compared to divergent boundary. Okay, so here we have the transform fault boundary. They tend to slide past against the other. And also, the interaction of divergent boundary with another divergent boundary produces the interaction of transform fault boundary, wherein they tend to slide past against the other. Okay, so here we have the transform fault boundary. Okay, similar to this one. Okay, so not just the divergent. Let's say, for instance, we have the interaction of divergent boundary and convergent boundary. Sorry. So we have the interaction of divergent boundary and convergent boundary may produce a transform boundary. Okay, so here we have transform boundary. So above, naatay divergent. Below, we have convergent. And the interaction of divergent and convergent produces transform fault boundary. Okay? So, the interaction of plate boundaries creates convergent, divergent, and transform. Okay? This was being triggered or powered by the convection currents happening in the outer core and within the mantle. Since the crust is just floating above the mantle, and the mantle is just floating above the outer core, if the convection currents happening in the outer core allows the movement of lithospheric plates, so the mantle moves followed by the crust. That's why there is a continuous movement of our Earth's continents. Okay, so the interaction of plate boundaries, as what you have noticed here. Let's say, for instance, we have divergent, divergent. They may produce transform fault boundary here in the middle, or they may produce convergent boundary on the other part of the moving crust. Okay, so every other boundary is connected to the other boundary, and they are also powered by the convection currents happening in the outer core. Okay, so I guess that ends the discussion. We're in plate tectonics and seafloor spreading allows the continents to move. That's why there is a continental drift or a continuous movement of continents, simply because they are being powered by the plate tectonics and the seafloor spreading. Okay? Without plate tectonics, without seafloor spreading, there is no continental drift. Without convection currents, there will be no plate tectonics. Without convection currents, there will be no seafloor spreading as well. Without convection, plate tectonics, and seafloor spreading, then there will be no continental drift. Okay? So, I guess this ends my discussion. If you have other concerns or clarifications, just message me through MS Teams and I will answer it immediately. So this ends my discussion. Thank you everyone for being around. Keep safe, God bless, and bye-bye.